So yeah, I'm Nathaniel Haines, also go by Nate. If anyone's met me, I'd probably introduce myself by either of those at the conference. Sometimes I get confused. Just not Nathan, that's the only thing that doesn't work. So I'm the manager of data science research at Ledger Investing. I'll talk a little bit more about exactly what that is on some further slides, because there'll be some examples that I share from the work that we do, so it's useful to know a little bit about the context. But yeah, today we're here to talk about BayesBlend. This is a library that we developed internally at Ledger and have been using for a little while, and then recently open sourced it this past summer. And so basically what this allows you to do is, it's geared towards Bayesian modelers, but you can, in theory, use this with other types of models. But the basic idea is that instead of doing model selection at the end of your workflow, you can blend together your various models to generate some predictions, as opposed to picking, the best one out of the set. And so that's the basic idea here. We're going to go through a little bit of context about kind of why we approach problems this way. I'm going to go through a pretty simplified example to kind of build some intuition and talk a little bit about the API for the library. And then at the end, I'll go through a practical example from the work that we do. So this is the insurance world. Very exciting. Probably most of us have some insurance. We are the insured down here. I have like a car policy, workers' comp, whatever it might be. We give money to the insurers. There's somewhere over 1,000 of them. There's a lot of insurers. They take all that money, they invest some of it, and then they pay us later if something bad happens. And then the issue with how this works, there's a lot of regulatory stuff. The insurer needs to have enough money to make us all whole if something terrible were to happen, say a hurricane or something else. And this presents a sort of problem for the insurer, because if they want to grow their business, they need a lot of capital in order to do this. And there are many ways that you can acquire capital, but the way that it's typically done in the insurance world is a reinsure, which, to put it in fancy words, because every time you go up, you get more and more money, which I hope is clear from what's on the slide here. But the reinsurer is sort of the same thing as the insurer from our perspective. They're just kind of a bigger version of the insurer. And that's a simplification. It's not exactly that way, but you can think of it that way. And the way that it works is they understand insurance, they understand the data, and so the relationship between these two, the insurer and the reinsurer, is such that they understand all of the data, how it works, how you can make money off of these portfolios of insurance policies, and so they're able to kind of come together and make these deals. But there's only really a handful of reinsurers. And so it's a pretty inefficient market because it requires a lot of knowledge to kind of be in their position. You need the capital and the knowledge. And so this is kind of where we come in. What we do at Ledger, we bring in institutional investors into this equation. So institutional investors, they have the money, they don't have the context or the knowledge. That's what we do. So we do all the modeling, pricing, things like that to kind of make this more efficient. Because the downside of inefficiency in any market like this is all of us as policyholders pay more money. It also makes it harder for insurers to write new business. So like certain parts of the market that you might not otherwise be able to insure get uninsured. If you know anything about the insurance world, there's this big gap growing between losses that occur and losses that are insured. It's a big problem, and so that's one of the things that we seek to do with all of this, is to make this all work. And so there's multiple steps in our workflow, and the first one here, loss development, has to do with like measuring historical performance of the insurance policies that are written. And then the second part is forecasting. I'll focus on loss development for a practical example later, so that's why I wanted to give some of the context here. But the thing, if we want to transition, it's not really a talk about insurance, just kind of throw it in here for the context. But what we do face, it's very similar to, I think, any industry, is that for each of these modeling stages, we have a variety of models that we might use. And some of these are based on different theories that people, like decision makers, might have. Some of them are just different models that are used in the actuarial literature. These aren't exactly the model names, these are some of the internal names that we use. But the basic idea, I think everyone is in a similar position if they're doing modeling at an organization, is that you might have a bunch of different models that all might work in some cases and not in others. Same for our various other steps. And so each step of the pipeline, you might have all these different ideas about how the world works, all these different models that perform better or worse. And the question is, how do you choose the best one? I mean, typically you might do some form of cross-validation, pick the one that performs the best, something like that. There's other cost considerations and things like that too. But what I want to try to convey today is that you don't need to choose, you can just blend them together. And so that's what BayesBlend is geared towards doing. So to walk through, we'll start with a little bit about sort of just the API usage of BayesBlend. And we're going to use a very simple example. So the way we can think about this is you're flipping a coin, we get some zeros and ones, and we have an increasing success probability across time. So if we can think of this length space function here, so across time, probability of success is increasing. It's literally a straight line. And later down here, we're doing some splitting up of the data just for a demonstration later. Here's a picture of what this looks like. Hopefully this is visible. I tried to make the font big, but Plotly likes to use small fonts by default, so I did my best. And so here we have the sort of true data generating process, if you will, it's that black line. And then you can see all of the different observations that fall. You typically see this when you're looking at like logistic regression plots or something like that. In theory, you can think of this as a logistic regression, it just happens to be flat. And so that's what our data looks like. And in the real world, things are much more complicated. But I think with this example, I want to approach this as if it's kind of like that situation as well. So we might approach this situation with a pretty simple model. And this model, I don't know, I mean, maybe show of hands, like how many people like do Bayes or are familiar? Okay, it's good, pretty good chunk. But this is essentially a logistic regression, if you want to think of it that way. But the idea here is that theta here is our parameter that we're trying to estimate, and it's really just a success probability. So this model is assuming just a static success probability across time. And so this model isn't really going to be able to capture the data, the true generative process very well. And then we have some prior that we set. A beta distribution is just between 0 and 1, and you can kind of move around where you think the actual value should be with these two parameters here, alpha and beta. Very confusing if you use a parameter that's the same name as the distribution, but we will ignore that for now. We use Sand to do a lot of this. I'm not going to get into this code. The only reason I'm really showing this is because, at first off, it looks kind of similar. You can kind of see in the model block the similarities there. But here, this is something that's important for BayesBlend. In order for BayesBlend to work, we need the log of likelihood associated with the test data in this case. This is very important. I'll talk about this a bit later, but basically we had our training data, our test data, and our validation data, those three different sets. All of these stacking models should always be trained on out-of-sample like test data. It's one of the big benefits. And so we generate our out-of-sample likelihood. This is just for the training data, so we're generating that repeat that for test and validation. And then we'll also have the posterior predictions. So we'll have out-of-sample likelihood, out-of-sample predictions. And then what we're going to do for this simple example is we're just going to have, we're going to have two models. They're just different sets of priors. And so our sort of low model, it's like a pessimistic model, has like a really high or concentrated mass on the low, like a low success probability. So we're assuming success is always relatively rare. And then the high model is just the flip side of that. And so we're going to take these two models, like fit them both to the data, and then use BayesBlend to kind of blend these models together to create something that we hope is better. So here's some code to fit this in command stand. Again, if you're not familiar with command stand, that's fine. I won't get into too much detail, but just want to show basically what's happening. We're compiling the model, getting all the data organized. Here are the different kind of model priors. We're just kind of flip-flopping that alpha and beta to make it high versus low. And then we're just fitting models. And so at the end, we just have this dictionary called fits, and that has the fitted models for both of these, kind of like this simplified example model here. So here's what happens. You look at the priors. You may have guessed something like this would happen. We have a bunch of the success probability increases over time linearly. So when you fit this, the posteriors get closer to central. So so closer to sort of an even success probability. And then if you remember back to what our sort of plot of the true generative process looked like, you can kind of plot out the model implied success probability on this plot to see kind of what it thinks. And so each of these models, it's like these are just different samples from the posterior distribution. And so, one of our models has the low success probability, one has the high. And we're going to try to do some blending to see if we can do better. We can better match that true data generating process. See, I gave that away already. And so the way we're going to do this is we're going to do something called model stacking. There's a bunch of different approaches that you can take. Like if you've ever done like things like ensembling. Yeah, question?
Yeah, this is probably a tough question, but maybe other people have it. So
yeah.
I'm confused about how your data generation is changing over time.
Yeah.
You're fitting it into a model that assumes it's not changing over time.
Right.
Can you help me make that link?
Yeah. Well, yeah, no. So the link is basically like often we're in a situation in the world where what's actually happening is quite complicated, and we have these simplified models, and so that's really all there is there.
Oh.
So yeah. So these are intentionally simple models that aren't capturing the true process there.
I see. The idea is like model blending will kind of help us capture that, even though our individual models are kind of ignorant of that.
Right. Yeah. Good question. So thanks for make sure everyone's So when there's multiple forms of model stacking, and this is one way that we can represent it. So here we'll have I as our data index, K as our model index, and I'll kind of just walk through what this looks like. At the end of the day, what we want to do is estimate weights that we use to kind of blend model predictions from different models together. In this case, we're going to have a different weight for each data point and for each model. In the simple case, you might just have a weight for each model, but we want it to be data point specific as well. So this is kind of just a more general form of stacking here. And so that's what this W here is. That's something we need to estimate from the data. And then here, this is just our out of sample likelihood. So like yi might be like a data point, an out of sample data point, and then y minus I over there is all the data except for I for model K. And so this is just when we split up our training, test, and validation data. This would be the out of sample. This would be like the test data likelihood. And so that's a value that we get from like fitting our models and extracting the test performance. And then down here, this is what makes stacking extremely powerful. And the reason I chose this specific example where you have these models that can't possibly capture this change over time, because we can actually build an arbitrary model on those weights. And so this is a pretty powerful concept. And one of the things that you can do here, for example, is have some sort of regression on the weights. So in this case, it's kind of weird because we have just like a softmax and all this stuff going on. But you can think of it as like a more general form of like a logistic regression or something like that, multinomial regression. And so we could have like alpha here having sort of different intercepts, so different absolute weights for each model, and then beta with xi here being like covariates of interest, which in this case, we can throw in time as a sort of covariate, and that's what we'll do in the example. And at the end of the day, what we're trying to maximize is after doing the weighting of the out of sample likelihood, we're just trying to maximize that quantity. In theory, your weights don't actually have to sum to 1 in stacking. Like classically, that was never an assumption you needed to make, but it is useful, makes it more interpretable. And we're going to do that here, hence the softmax. But that's basically it. There's a lot of different ways that you can go about fitting these models. And in BayesBlend, there's different approaches you can take. Like you can just run an optimizer on this. You can use like LUIC or other types of weights, like AIC, BIC types of weights to get weights for blending purposes. But in this case, we're actually kind of fitting Bayesian models to get the weights as well. So it's kind of Bayes all the way down. And so to do this in BayesBlend, so here we're just importing the hierarchical Bayes stacking, which is the form that allows you to actually kind of estimate like with covariates included. And here we're creating this time variable again, like in the real world, we wouldn't need to do this. Like we have some covariate already that we might hypothesize could arbitrate between the models in some way. And then we're splitting it up into the training, test, and validation data the same way to match the Ys. And then in this case, we fit the models, like the fits object here is just 2 command stamp models. It could be some other form of models, but in this case we have this from command stamp pi method here that just makes this a little easier. You can also work with, there's like a from RBiz method that you can use if you have other models fit with whatever other type of Bayesian software you're using, and you're able to convert it to RBiz. You can use this same general recipe here. And then we're pulling out the test log likelihood and the test posterior predictions. And then we're entering in for our covariates this time kind of covariate, which we sort of just made up, and we're kind of abusing the fact that we know a little bit about the data generating process here. But that's the basic idea. So we specify the model, and then you have this, we actually fit the model, you do your little kind of dot fit here. And so I'll take you back. Remember, this is what we had before. And after blending, you might kind of guess what might happen here. But after blending, the implied success probability looks something like this. So you get kind of more of this logistic curve that you're seeing. It's not perfectly kind of interpolating between the models, but that's because there is some, there's some priors at work inside of the actual stacking model itself that leads to some sort of regularization. But this looks a lot better than what we had before. We're actually accounting for some change over time, post hoc, after fitting these models, these candidate models that actually have no mechanism in them to do such a thing. And so that kind of illustrates the power of this type of approach. And then what I want to show here gets a little bit more into the weeds, but one of the reasons we need a validation set is because we fit our candidate models to the training data, and then we fit our stacking models to the test performance. If we really want to evaluate if this model is going to work in like a real world setting, we need that validation set to compare it to like what the candidate models would make predictions on that data set as well. And so what we're doing here, up here we're just kind of extracting all of that information. In BayesBlend, you basically have the various different models and then these draws objects. And the draws object is really just a container for the posterior, like the likelihood and the posterior predictions. It's a very simple object. All it has is those 2 objects inside of it. And that's just our internal representation that we use to do the fitting, do the blending, and all of that. And so in this case, we have a method where you can extract out those validation draws directly from command stamp pi. Again, you can also do like from RBiz, something like that if you're using RBiz. And we do that for each of the candidate models up top. And then down here, we're doing the dot predict on the validation data for the blended model, adding in the covariate there to make those predictions. We're putting all of this in one dictionary so that we can plot out some interesting stuff. And then if you're doing Bayes, you might be familiar with this quantity here, ELPD, or expected log pointwise predictive density, as we love to say. I think I got that right. It's always hard to say live. But the basic idea is this is just a log score for the model, and it's a sum over all the data points, and then we can compute some standard errors too. And here, I'm just plotting that out. And so you can see higher is better. In this case, it's a log score. It's not a negative log score. And so stack here is doing quite a bit better than the other 2 models, as we might expect from that plot that I showed before. Okay, so that goes over a little bit about the API usage. It's just some general usage there. I'm going to move on to sort of a practical example where I won't actually be using the API so much there. So I wanted to, maybe before we move on there, ask if anyone has any questions about that. Yeah.
So, but I think the 2 models, you are kind of using the knowledge that your results might vary over time, right?
Mm-hmm. Yeah.
And what if you just had a model in the first place that
Yeah. I knew this was going to be coming, right? So it's a great question. And like really we wouldn't. Like in that situation, we would literally never do that. That would be, I can't really think of a good reason as to why you just do that in a simple logistic regression style model, right? I think there's like two reasons, and there's like a practical reason, and there's more of a theoretical-ish reason. The practical reason is like in the real world, you might be fitting like quite complicated candidate models. They might already be baked in, like a lot of hypotheses and like things might be baked into those models individually. They could be very different in like functional form or other things like that. And the only way you can really get away with kind of doing the same thing that blending will allow you to do in that context is to sort of like do a full-out model expansion, maybe like build a mixture model of the two. And just practically sometimes that's infeasible. Just you get some issue estimation, lots of other things that can come up. So really I'd say it depends on the complexity of your model from a practical perspective. Theoretically, the benefit that we get from stacking is that, like in that case, you would be fitting your model to training data. And what stacking is doing is you're fitting to out-of-sample performance. And so by optimizing on out-of-sample performance, there's some rationale for like why that might give you better performance than even like a mixture model. And so that's the way that I into that. So thanks for asking. Not a plant. Yeah.
Yeah, another like basic question.
Yeah.
Now you have 3 models.
Yes.
Why not just like keep stacking?
Yeah, no, I think it's true. I think we've talked about this before actually. Now it's easy, right? I can just keep going. I think the limit ends up eventually being like how chopped up you need your data to be to keep going. But yeah, like in theory, you could just kind of blend 2 blended models, and there's really nothing stopping you. Although at the end of the day, you still would need in production to make predictions from all of the lower level candidate models, and then you'd have to like. So I think maintainability might be my first concern. Yeah.
An extension of that question, how would you ensure that your stacking model is still also interpretable when you need to go back to your stakeholder and say, this is what model versus...
No, that's an excellent question. So I think we would still normally interpret the model through the lens of like the candidate models. And so it's like, if I go back and I can understand each individual model, and then I know like what weights are assigned to each data point for the stacking model. So that's something you can do. I don't have actually an example of this, which now I'm realizing I should have, but you can just, after you have your model fitted, you could do like higher stacking fit dot weights, and it will just give you all the weights associated with each data point, something like that. And so I think from that perspective, you can still interpret the candidate models, but then if you're explaining the predictions, you can say like, all right, we understand each of these models, and then we're just weighting them together like this. Yeah.
Kind of back to the question about like when is too many models if you're continuing to stack them. Mm-hmm. Is there sort of a rule of thumb for like trade-off when it comes to overfitting versus accuracy?
Yeah, I think it's probably depend mostly on context. I would say generally you like 2 models you can make it work, but you do need to do some regularization there, which is why we got sort of that result that I was showing before. But generally, like the more you have, ideally what you want is models that have predictions that are different and not too correlated. Because if you have models that have like the exact same predictions, it doesn't matter.
Right.
And so ideally you have models, they might, like one model might be much better in terms of like RMSE than the other, but as long as that's not, the errors aren't correlated, you seek to gain something from the blending. So I think that's kind of, it's maybe a heuristic way to think about it, but yeah, no doubt. Cool. So I'll move on to the practical examples so I don't get run out of time here, but this is that first stage that we're often dealing with, where the 2 stages, as if I can summarize them, are just to measure historical performance and then to forecast future performance. And historical performance, even in insurance, is very difficult because this is how we typically look at the data. You can think like if accident year here, on this y-axis, is the year in which an accident occurs. Insurance companies gotten all the premium associated with this already, but they may not have paid out all the claims associated with it quite yet. And so we think in terms of a loss ratio, which is the claims paid out or like the losses associated with a portfolio versus the premium taken in. And so we want this to be lower generally, or less accidents too. That's good. But what happens, if it's like a workers' comp claim, for example, they could be paying out losses for decades. And so we have to look basically when we're in the future looking back at any given accident, or accident year in this case, we don't really have a full picture of how it's going to develop or where it's going to end up. And so this is kind of the problem that we're facing is we call the development lag, like how many years ahead we're looking back at a given year. And we index out with n, like we want to know what's happening at n equals infinity, essentially. And so this is our first problem that we approach. And traditionally, like actuaries will approach this by kind of just taking the ratio between these consecutive columns here, and you'll get like a factor that you can multiply out. And so you get this h to h factor is what it's called. And you can keep doing this and go out, and hopefully at the end it's 1, so that means nothing is changing past the data you have available, because this triangle, as we call it, gets smaller and smaller the less history you have. And it needs to asymptote at some point. If it doesn't, you kind of have a problem. And so that's one of the reasons that we use Bayesian modeling in this case. We want to get this number, but sometimes we're not always able to. And so I'll walk through a form of model that we use in this scenario. And again, if anyone has questions or clarifications for this part, let me know. But the basic notation here is we have a loss ratio for whatever index, wherever we're at. And we think it's distributed following a gamma distribution, which has a lower bound at 0. It's kind of like a log normal almost if you squint. And so this number doesn't go below 0, because that would mean that, it would mean that they paid out what would have to happen. They'd have to give you money. Yeah, it just doesn't work that way. You'd be paying negative premiums. And so this gamma distribution here, we're parameterizing it with like a mean variance parameterization for simplicity, because gammas are weird. So you can just imagine this like mu, and then here's the mean that we expect, and sigma is the standard deviation. And that mean, this is following from the model that we had before, where we have this h to h factor that we multiply by the loss ratio and that kind of, and multiply it out across columns there to get what we want. And so that's why we have 2 indexes for the loss ratio, because it kind of depends on the previous one. But we only have 1 ATA for each column here. And then what we're doing here to kind of impose this constraint so that this does asymptote to 1 eventually is to say, okay, there's just this exponential decay with increasing development lag. So as years go on, it decays to 1, so plus 1 at the beginning. And that's how we estimate these ATA factors. And then finally, another important piece here, and this is why Bayes is pretty cool, is that, well, we can say too, like there's this observation error that we have here, this variance in the gamma. We can also make that go to 0 as time goes out. Because, if it's year 3000 and we're looking back at year 2014, we're pretty certain what the loss ratio is. And so the model here kind of encodes that. And so, in the insurance world, I'm not an actuary, so I don't like to say mean things. But there's a lot of heuristics that are used, and partly because sometimes, actuaries are mostly working in Excel, and there's like limited capabilities with what you can do. And a lot of times you might be in a similar situation like this, and one of the methods that we use is to say, well, the model might fit differently depending on like how much of this history that we use, and so they might try different styles, different parsing up of the data, fit the model various times. This is something that's common in any field, I would say. And so we can kind of mimic that process like this. We can say, all right, for our first model, we're going to take this and we're going to fit it to all the historic data. For our second model, we're going to just cut off that first part where there's a lot of volatility usually. Like the first year, there's maybe a lot that goes on, a lot that changes. And then we can kind of keep doing that. So we'll have 4 models that we just use various different parts of the data to fit to. So we do that, and I'll go through this. There's kind of like this little study design. It ends up being quite a complicated example, so that's why I'm kind of going a little over and putting it here like this. But the way that we're going to do this is we actually have this data from 1988 to 1997 for 50 different insurers. So we have like 50 of that triangle, imagine. But we have the full square. So we know the history. It goes out like 10 years, and that's enough in this case to kind of reach some asymptote. And for the sake of this example, for simplicity, instead of like kind of partitioning up the triangle in a weird way. We're going to fit everything up to the 7th dev flag there, and then our test data is going to be dev flag 8 and 9, and then our validation will be just the last one. It kind of makes it easier to talk about as opposed to talking about diagonals and all that. So we're going to fit all of those, and then we're going to fit a hierarchical stacking model to the test data from all of those at once to blend them together. And then we're going to include the accident year, and then also the development lag, just as discrete covariates, because why not? And so here's an example of what the predictions coming out of that dev flag 4+ model look like across these different accident years. I'm highlighting the test data points in white and the validation in red. They're pretty good, not too bad, I would say. Now, you're going to have to keep a very close eye. I'm going to show you like the blended result, and you're going to have to keep a very close eye, mostly the end. So if you look at the red dot, what you're seeing here is like a 90% interval that's shaded, and just like squint and watch what happens to the interval when I go to the next slide. It gets a little thinner. Now, part of that is because this model has, there's a lot more data that's going into fitting, but then there's also the optimization process where we're optimizing for the fit on those white data points, which are towards the tail end here. And so you'll also kind of see some interesting stuff where, like this model isn't capturing some stuff as well at the very beginning than the blended model is, because it has some of those other models in it that were actually fitted to those data points. Yes, question?
Sorry, wouldn't a more fair comparison would be like a 4-year look that's fitted up through year 9 and predicting your time?
Fitted up through...
Because the blended model is fitted on years 8 and 9.
Yes.
So it makes sense that you're more uncertain in year 10 because you're only fitting year 9.
Oh, yeah. So I'm just showing against that one model. But I think what I was going to show, so on this next slide, is a little bit more comprehensive, where this is like that ELPD if you look at the column here. So I fit a bunch of all the different models. You can fit in BayesBlend, so I'm showing all of those, but the hierarchical stacking one is right here. And you can see, so this is like the dev like 4, 3, 2, and then 1. And 1 does a lot better because it's fit to more of that history. But you'll still see like even still, like the hierarchical model, the blending model, with those covariates in it is pushing a little bit beyond that. There's also some interesting stuff here for some other methods that you can use to derive weights, where actually some of these other blended models are performing worse than any of the models in here. So like the Pseudo-BMA, for example, up there. And the reason there is because we kind of dived into that, and this is getting pretty technical, but with the, when you're looking at ELPD, there was like an outlier point for one of the models, and up here, the way that Pseudo-BMA works is very sensitive to those outliers, where stacking is not. And so stacking is kind of like a much more robust way to deal with model blending than some of these other more classical methods.
Can you give us a little insight into what these are at that level?
What are exactly?
Different types of blending?
Yeah, so Pseudo-BMA is like, if you have like you do like the leave one out, or you get like the AIC, BIC, LUIC, all those information criteria weights. Pseudo-BMA is basically just a soft max on that. And that's how you get a weight for each model. So it's like not per data point, you just get like one weight per model. That's what that is. And that, when you're doing that operation, when you take the sum to get like the ELPD values to do the softmax, and then the sum is just very sensitive to an outlier, just like a mean is. And so that's what the Pseudo-BMA is. Pseudo-BMA plus is the same thing, but bootstrapping the original data first. Stacking MLE is, imagine the stacking formula we had up there, but instead of covariates, you just have one weight per model. And that one, you estimate the weights per optimization, as opposed to like fitting a Bayes model. And then stacking Bayes is the same as the one, like the MLE version, you're just fitting it in standard. And then hierarchical is the only one it's the one I described with the covariates. Yeah, thanks, yeah. So, and then over on the left, it's just showing sort of like the blended result across all of the validation data. So it's not super informative, but yeah, so that's a little bit about, I know I kind of rushed through the practical example there, but happy to talk in more detail. That is all I have.
So happy blending.
I don't know how many people will get this right.